In this video, we discuss Rolle's theorem, which provides the conditions necessary for a given function to have a horizontal tangent line on an interval. So here's the statement of the theorem. It says, let f be continuous on the closed interval from a to b. And differentiable on the open interval from a to b. Then if f of a equals f of b, we're guaranteed the following. Then there is at least one x value, which our textbook authors and many textbook authors label with the number or the variable c. Then there's at least one x value c in the interval from a to b, and this is just notation. That means c is in this interval, satisfying the following. F prime of c is equal to 0. Okay, so let's think about what this means and what I just told you. This is a theorem that provides the conditions necessary for a function to have a horizontal tangent line on an interval. So let's go through this and identify the conditions. Here are the conditions. It says, let f be continuous on the closed interval from a to b. So we have to be talking about a continuous function. And remember our intuitive definition of continuous. That means the whole graph can be drawn in one piece. You can draw it without lifting up your pencil. And it's continuous on a closed interval from a to b. So it's well-defined at a, it's well-defined at b, and it can all be drawn in one piece from f of a to f of b. Now we're also told that it has to be differentiable on the open interval from a to b. Now remember what differentiable means. That just means the derivative exists, which means the derivative is a well-defined function for all of the x values between a and b. And what that means for us geometrically is that the function doesn't have any sharp corners on the interval from a to b. If it's differentiable, or first of all, if it's continuous, it can be drawn in one piece. If it's also differentiable, that means it's nice and smooth. So I've got a function that is all drawn in one piece that's nice and smooth on the interval from a to b. If it's continuous, it's smooth, and we're on a closed interval from a to b, and the following is true, fourth condition. F of a is equal to f of b. If all of those conditions are satisfied, then we're guaranteed at least one x value c in the interval from a to b, such that the derivative at c is equal to 0. Now remember what this means. If we're saying that the derivative is equal to 0, that means the function has a horizontal tangent line, or the graph of the function has a horizontal tangent line at x equals c. So we just have to check the four conditions. Then if those four conditions are satisfied, then we know for sure that there's one x value out there where the slope is 0, and that x value lies in the interval from a to b. We're guaranteed at least one x value in the interval from a to b where this is true. Now let's draw some pictures and make sure we understand what this is telling us. Here's the idea. We're saying f is a continuous differentiable function on the interval from a to b, and f of a and f of b are the same. So the y value at this x value and the y value at this x value, the y value at the left endpoint and the right endpoint, both of those y values are the same. So maybe they're both equal to this. And now we're told we've got a continuous differentiable function, so it's all in one piece. And it's nice and smooth, so there are no sharp corners. Well, here's the idea. If I start here and I end here, if my function goes up, it has to go down sometime if it's going to go back to that y value over there. And if it goes down and I'm guaranteed that it's smooth, so the tangent line is well defined, well then there has to be an x value where it tops out, where it achieves that maximum. Or maybe it goes the other way, it might achieve a minimum. But we're guaranteed that we have a tangent line that's horizontal. If the function goes up, it has to come back down. And that means there's an x value where that slope is 0, and we'll call that x value c. Now the other possibility is this. If the y values are the same, and our graph is nice and smooth, the y values are the same at the endpoints, so f of a and f of b are the same thing, and the function goes down, well then it has to come back up sometime if it's going to be at the same y value at b that it was at a. So that means if it goes down and then it has to come back up, and we're guaranteed that it's nice and smooth because it's differentiable, there must be some x value in between a and b where the slope is 0, where that tangent line is horizontal. Now, this problem statement says, or excuse me, not problem statement, this theorem says that if f is continuous, so it's all drawn in one piece, and we're on a closed interval, so it's well defined here and here, and the function's differentiable, so it's nice and smooth on the interior of the interval, and the y values are the same. It doesn't say that there's one c value, it says that there is at least one c value. So we're guaranteed that the picture looks, at a minimum, it's going to look like this. If it goes up, it has to come down. If it goes down, it has to come back up. And since it goes up and down smoothly, we're going to have a 0 tangent at the top, or a zero slope at the top, or a 0 slope at the bottom. Now, it's possible that it doesn't just do that once, it might do that multiple times. So maybe your graph looks like this. Maybe we started at x equals a and we ended at x equals b, and the y values are the same, and the function is continuous and differentiable on the interval. So Rolle's theorem applies. It might go up and then go down and then go up and then go down and then go up. It might look like that. If the function's continuous and differentiable, this time we're guaranteed to have at least one value, x equals c, on the interval where the slope is 0. But we might have more than one c value. And we have a 0 slope at the top there, and at the bottom here, and at the top there, and at the bottom there, and at the top there. So we actually have 1, 2, 3, 4, 5 c values. I'll call this one c1. I'll call that c value c sub 2. This one is c sub 3. This is c sub 4. And this is c sub 5. Now the theorem guarantees us one of them. It says if we start here and we end here, if our function goes down, or if a function goes up, it has to come down. If a function goes down, it has to come back up. And if it does so in a smooth way, we're guaranteed to have a horizontal tangent line. Now we might have lots of horizontal tangent lines. We might have 5 of them, like this picture. Now another possibility for a function that satisfies Rolle's theorem is maybe it's a really boring function. Maybe there's not really a lot going on at all. Maybe at x equals a and x equals b, the y values are 7 or something like that. I don't know what they are. But they stay 7. If the function itself is a horizontal line, there are infinitely many points where the slope is 0, because the slope of the whole function is 0. So this is satisfied for every x value between a and b on in this picture. So that's Rolle's theorem. We're guaranteed that if we're on a closed interval, a closed finite interval like this, the function's continuous, so it can be drawn in one piece, and differentiable, so it's nice and smooth, and the y values are the same. There's at least one x value where the slope is 0. it might be there, or it might be there. There might be 5 of them. There might be some finite number of them. Or it might be the case that we've got infinitely many of them. If any part of our graph is horizontal like this, we've got infinitely many x values where that slope is 0. So that's Rolle's theorem. And these are the pictures that go with Rolle's theorem. That's what I want you to think of whenever you think of Rolle's theorem. Now, it's possible that Rolle's theorem doesn't apply. If any of these conditions isn't satisfied, Rolle's theorem doesn't apply. So maybe I've got a function like this. We're on the interval from a to b. The y value at a and the y value at b are the same. Maybe the graph looks like that. Or maybe the y value at a and the y value at b are the same, and the function looks like that. Now, Rolle's theorem says that if all these conditions are satisfied, there's at least one x value on the interval from a to b where the slope is 0. But this one doesn't have a 0 slope anywhere. Does that mean I lied to you? No. The theorem wasn't satisfied. All of the conditions don't hold here. We have to have the function, or the function has to be continuous for this to work. These functions are continuous. That's fine. The function has to be on a closed interval from a to b for this to work. These functions are well defined on a closed interval from a to b. And here's the part that doesn't work. The function also has to be differentiable on the closed interval from a to b. That sharp corner there and that sharp corner there mean the function is not differentiable. So even though the y values are the same and the function is continuous, the fact that it's not differentiable means that Rolle's theorem does not apply. I'm abbreviating theorem with THM. Now, watch this. The theorem says if the function's continuous and differentiable and we're on a closed interval and the y values are the same at the endpoints, then we're guaranteed that there is an x value where the slope is 0 on the interval from a to b. Now, Rolle's theorem does not apply to this. So there is no x value, and it just so happens that there is no x value where the slope is 0. Now, Rolle's theorem does not apply to this either, but there are actually 2 x values where the slope is 0. So there's an x value where the slope is 0, and there's an x value where the slope is 0. I'll call those x1 and x2, x sub 2. But Rolle's theorem doesn't apply here. So if Rolle's theorem doesn't apply, that does not mean that you don't have a 0 slope. You might have a 0 slope or you might not have a 0 slope. Rolle's theorem says under these conditions we're guaranteed there's an x value on the interval where we have a 0 slope. If the conditions aren't satisfied, we might not have any points where we have a 0 slope, or we might have a couple of points, or we might have a point where we have a 0 slope, or maybe more than one point like we have here. So if the theorem doesn't apply, we really don't know if the function has a 0 slope on the interval from a to b or not. So in these 2 examples, Rolle's theorem doesn't apply because the function is not differentiable. It might also be the case that Rolle's theorem doesn't apply, but for a different reason. Maybe we're on the interval from a to b, and maybe the graph looks like this. The function is well defined on the interval from a to b. The derivatives exist over here and here, but two things. At this x value, the function is discontinuous. We're only guaranteed this if the function is continuous on the closed interval from a to b. And if a function is discontinuous at a point, it's also not differentiable at that point. So on this one, Rolle's theorem does not apply. Because f is not continuous. On the closed interval from a to b. Now, if f is not continuous, it might be the case that we've got a zero slope somewhere on that interval, or we may not have a zero slope on that interval. We can't tell. The theorem doesn't apply, so we can't go any further. Not with that theorem anyway. So maybe the function looks like that, and the theorem doesn't apply because of lack of continuity. The function might also be discontinuous for a different reason. Maybe the function has an asymptote. Maybe the y values are the same at the endpoints. But we've got a discontinuity at, let's call that x equals d. This is an infinite discontinuity, and that infinite discontinuity occurs on the interior of that interval. So d is in the interval from a to b, and the function's discontinuous there, so Rolle's theorem does not apply. Okay, so if the function fails to be differentiable, the theorem does not apply. If the function fails to be continuous, the theorem does not apply. Now, another option is this. The function might be differentiable and continuous, like this line segment. Actually, let's do this. Let's not make it a line. See the problem? It's continuous, it's nice and smooth, so it's differentiable, but the y values at the ends are not the same. So Rolle's theorem doesn't apply to this because f of b is not equal to f of a. Here's f of a, and there's f of b, and they're not equal to each other, so Rolle's theorem does not apply here. And there's sort of a combination of this one, and also the closed interval thing. Maybe this is x equals a, and this is x equals b. If the graph looks like that, well, that function is not defined on the closed interval from a to b. It's defined at a, but it's not defined at b. So f of a and f of b can't be the same thing. It is one continuous piece, but it's continuous on the interval from a to b, not including b, because we've got an asymptote at b. So Rolle's theorem doesn't apply here because this is not satisfied. This isn't satisfied because that right endpoint is not included. The function does look differentiable though, except maybe at x equals a there might be a vertical tangent line there. Can't be sure without the equation. Okay, so that's Rolle's theorem. That's the idea of Rolle's theorem. Now most of the time you're not going to be given these pictures. You're just given a function. You're given y equals f of x. And there's a reason why we call this class Analytic Geometry and Calculus 1. Analytic geometry is about the connection between that function, that equation that you're used to looking at, and the graph. So we're going to be given an equation, and we will be able to infer something about what the graph looks like using all of the tools that we've learned in algebra, trigonometry, and Calculus 1, including Rolle's theorem. So these pictures won't be given to us, but we can do some calculations and we can draw these pictures ourselves. So let's work some example problems that relate to Rolle's theorem, and keep this picture in mind. If your function's continuous, you're on a closed interval from a to b, and the function's differentiable, and you start and end at the same place, so the y value over here and the y value over here are the same. If the function goes up, it has to come down. If the function goes down, it has to come up. If it does so in a smooth way because it's differentiable, you're guaranteed at least one x value where the slope is 0. Now you might have a bunch of x values where the slope is 0, or you might have infinitely many x values where the slope is 0. And then these are all of the ways that Rolle's theorem would not apply. If the function fails to be differentiable, it doesn't apply. If the function's not continuous, it doesn't apply. If the function value on the left and the function value on the right are not the same, it doesn't apply. And that's sort of a hybrid of a number of these cases. Okay, so keep this in mind. We need to check 4 conditions. We need to be on a closed interval from a to b. The function needs to be continuous there. It has to be differentiable there as well. That means the derivative must exist for every x value on the interval from a to b. And the y values at the endpoints have to be the same. If that's true, then we get at least one x where the slope is 0. Maybe several x's, or maybe infinitely many x's. Okay, so let's apply that to a problem. This is a typical problem statement for Rolle's theorem. It says, determine whether Rolle's theorem can be applied to the function f on the interval from a to b. If the theorem can be applied, find all the values of c in the interval from a to b such that the derivative is 0. So we're looking for the x values where we've got horizontal tangent lines. So where the graph is going to look like this. If Rolle's theorem doesn't apply, explain. Okay, first of all, we need, if we're given this function on this interval, we need to check the conditions of the theorem. Always start there. And we've got 4 conditions for our theorem. First, we've got a closed interval from a to b, so that's satisfied. Now we need to make sure that f is continuous on this closed interval from a to b. So we'll say f is a polynomial function. Now, it might not be obvious that this is a polynomial function right now, but remember from pre-calculus that this is a polynomial function in factored form. If I write this twice in FOIL, I'll get x squared plus 4x plus 4. If I take x squared plus 4x plus 4 and I multiply it by the quantity x minus 4 and I distribute and collect like terms, I'm going to have a cubic polynomial in x. I'll have x cubed plus a constant times x squared plus a constant times x plus a constant. So this is just a polynomial. It's just been factored for us, which is nice. So polynomials are well defined all the time. So we can say yes, f is continuous on the closed interval from a to b because f is a polynomial. One other thing that you can check for continuity is domain issues. Anytime you're given a function as a single equation, so it's not a piecewise function, but it's just defined in one piece using familiar functions that you've studied before. So polynomial functions, root functions, exponential functions, logarithmic functions, trig functions, inverse trig functions. If your function over here is defined by a single equation, there's an implied domain with that. The functions that we've studied in our classes are all continuous on their implied domains. With the implied domain, there are basically three things you have to watch out for. You don't want to divide by 0, you don't want to take even roots of negative numbers, and you don't want to take the logarithm of a negative number or 0. There are no logs here. There's no division, so I'm not going to divide by 0. And there are no even roots of negative numbers, or no even roots of any numbers. So checking those domain issues lets me know immediately this function is well defined, and therefore, because it's defined by one single equation using those familiar functions we've studied before, this function is continuous on the interval from -2 to 4. So we have to check 4 things. Here's our theorem. We need to check continuity. We need to be on a closed interval. Check. We need the function value at one endpoint and the function value at the other endpoint to be the same. So the y values at the ends are the same. And then we need to check differentiability. So we just checked continuity. By considering domain issues and the fact that it's a polynomial. Now let's check the endpoints. F of -2. So if I substitute in -2 for x, well, this is just -6 times 0 squared, which is of course 0. And then if we substitute in 4 for x, we get 0 times 6 squared, which is of course 0. So f of -2 and f of 4 are the same, so that condition is satisfied. Both of them are 0. And the last thing we need to check is differentiability. We want our function to be nice and smooth on this interval. Now, polynomials are always nice and smooth. If you graph them, there are no sharp corners in any polynomial functions. So we could just say f is differentiable because it's a polynomial. That's a possibility. Or we could just take the derivative and talk about domain issues the way we talked about them before with continuity. So let's do that just to practice that. I know it's going to be differentiable because it's a polynomial, but let's prove it. F is differentiable on the open interval from 2 to 4 because f prime is well defined, and let's prove it. So f prime of x is the derivative with respect to x of x minus 4 times the quantity x squared, or x plus 2 quantity squared. Now you've got some options with this. If you want, you can write this twice in FOIL, distribute the x minus 4 to that, and then take the derivative using the power rule. Or you can use the product rule. I think in this case I would rather use the product rule. So I'm going to call this my first function and this my second function and apply the product rule. The derivative is the derivative of the first function, and then we multiply by the second function, undifferentiated. And then we add the derivative of the second function times the first. And we just evaluate these two derivatives. Derivative of x minus 4 is just 1 minus 0, so 1. And this derivative requires the chain rule, or you could write it twice in FOIL and just use a power rule. I'll use the chain rule so that we can practice with our chain rule. I've got a function x plus 2 nested inside this squaring function. So I'll use the chain rule. The derivative of a function squared by the chain rule is 2 times that function, and you multiply by that function to the 1 less power, but 2 minus 1 is just 1. And then you multiply by the derivative of the inside by the chain rule. And the derivative of x plus 2 is just 1. So this simplifies to x plus 2 squared times 1, which is just x plus 2 squared. And then over here we've got a 2 and an x plus 2 and an x minus 4. So I said f is differentiable because f prime is equal to this and what? Well, we need to make sure this is well defined for all x values on this interval. Well, sure it is. There's no division by 0. There are no even roots of negative numbers. There are no logarithms of negative numbers or 0. So we'll say f is differentiable because f prime is well defined for all x in the real numbers, and particularly we're interested in the x in the interval from -2 to 4. So our 4 conditions are satisfied. We're on a closed interval, the function's continuous, the y values on the ends, I wrote f of -4, that should be f of 4. The y values on the ends are the same, they both happen to be 0, and we said that f is differentiable. On the interval from -2 to 4. Okay, so we were asked to determine whether the Rolle's theorem can be applied to f on the interval from a to b. It can, because it's continuous and it's differentiable, and the y values at the ends are the same, and we're on a closed interval from a to b. And the question says, if the theorem can be applied, and it can, find all values of c in the interval from a to b such that the derivative is 0. I almost hate that they're using this variable c, because people are like, what's c? It's just an x value. They're asking us to find the x values on the interior of the interval that give us a 0 slope. And then we're going to call those x values c values instead of x values, but it's the same thing. So our 4 conditions are satisfied. So Rolle's theorem applies. And now we want to find the values of x that make the derivative 0. So you're just going to set the derivative equal to 0 and solve for x. And I'll write that on the side. So our goal is to find x values in the open interval from -2 to 4 that satisfy the following. F prime of x is equal to 0. And we'll call those x's c's later. Okay. So I've got f prime equals x plus 2 squared plus the quantity x plus 2 times x minus 4. And we're looking at this, and we're saying to ourselves, well, what do these guys have in common? Well, this has an x plus 2 in it, and this has an x plus 2 in it. So I can factor out an x plus 2 from both of those. And then I say to myself, x plus 2 times what gives me x plus 2 squared? So, or x plus 2 times what gives me my first term? That's another x plus 2. And then I say to myself, x plus 2 times what will give me my second term? Well, it already has an x plus 2. I need a 2. And I need this factor of x minus 4. Don't forget the parentheses, because that 2 has to distribute to it. Okay, so f prime is equal to this. If we distribute the 2 over here, we get 2x minus 8. And I've got a graph all set up for us. We're going to graph this in a little bit. F prime of x is x plus 2 times the quantity x plus 2 plus 2x minus 8. And let's simplify this. x plus 2x is 3x, and 2 minus 8 is negative 6. Well, I can factor out a 3 from those. 3 times x gives me 3x, 3 times negative 2 gives me 6, and normally we don't put the coefficients in the middle like that. We like to put our constants out front. That's just convention. And so we get f prime is equal to this. Now that it's factored, it's easy to set it equal to 0 and solve for x. Now this times this times this equals 0 if one of the factors is 0. It's the only way we can get 0 out of a product is if one of the factors are 0. Like if these were 3 negative numbers, a negative times a negative times a negative would be a negative. If all 3 were positive, we get a positive. If 2 were negative and 1 was positive, we'd get a positive. If 1 was negative and 2 were positive, we get a negative. But there's only one way to get 0. The only way to get 0 is if one of these guys is 0. So we would set 3 equal to 0, but 3 is never 0. We'll set this factor equal to 0 and that last factor equal to 0 and solve for x. Now, we're looking for x values in the interval from 2 to 4 because we're looking for c values. C values and x values are going to be the same thing, where the slope is 0. So this negative 2, that's an endpoint of our interval. It's not on the interior of the interval, so this is not what we're looking for, but that is the c value we're looking for. So I would just write x equals 2. If you look up the answer in the back of the book, they would probably write c equals 2. That's the x value where you get 0 slope according to Rolle's theorem. Now we're done with that problem. As far as the textbook is concerned, we have answered the question. We've determined whether Rolle's theorem can be applied by checking the 4 conditions of the theorem. And then we found the values of c that give us a slope of 0. But I would like to visualize this. I want you to see Rolle's theorem. So to visualize this, I'm going to graph it. F of negative 2 turned out to be 0, and f of 4 turned out to be 0. So if we graph that, when x is negative 2, we get 0. When x is 4, we get 0. So those are the points. And we're only interested in this function on this interval from negative 2 to 4. Now at x equals 2, we're told that we have a 0 slope. Or we're not told that, we calculated that. We get a 0 slope when x equals 2. To figure out what the y value is there, let's substitute this x value into the original function. So I have 2 minus 4 times 2 plus 2 squared. So that's negative 2 times 4 squared. So negative 2 times 16 is negative 32. Ooh, this is going to be very much not to scale. Yeah, so not to scale, we'll say that's negative 32. And we get this. We get a 0 slope over here at x equals 2, y equals negative 2. I don't know exactly what my function looks like, but it might look something like this. Notice that it's continuous on the interval from negative 2 to 4. It's nice and smooth. If I drew my picture well, I would see at c equals 2, we have a 0 slope. The y value happens to be negative 32 there. So all of the conditions of Rolle's theorem are defined. It's continuous. The y values are the same at the ends. It's nice and smooth. So we're guaranteed to have at least one x value between negative 2 and 4 where the slope is 0. It turned out that the x value between negative 2 and 4 where the slope was 0 was x equals 2. Okay, so that's Rolle's theorem. That's what we do when it applies. Let's look at some other examples. Same question, different functions. Question is still, determine whether Rolle's theorem can be applied to the function on the closed interval from a to b if the theorem can be applied, find all the values of c in the interval from a to b such that the slope is 0. If Rolle's theorem doesn't apply, explain. So remember what you're doing. You're checking all of those conditions. Because if the conditions don't hold, we're not guaranteed anything. So we need to be on a closed interval from a to b, and for all of these problems we will be because we were told the closed interval from a to b. Now we need to check continuity. F is continuous. You might say, how do you know? Well, we're going to check for those three things. Division by 0, there are no x values that cause division by 0, so we're fine there. Even roots of negative numbers. Now you might be tempted to think there's an even root here, but there's not. Remember, this number in the denominator is the index of the root. So that's really the cube root of x squared. And that's not an even root, that's an odd root. So we don't have to worry about even roots of negative numbers because we've got an odd root, not an even root. And we can't take the logarithm of a negative number or 0, and there are no logs in this. So f is continuous. And we'll say f is continuous because it is well defined on the stated interval and it's given by a single equation. It's just a difference of two continuous functions. It's not a piecewise function, so since it's well defined, it is continuous. Alright, so we need to check continuity. We also need to check differentiability. So compute f prime. F prime is the derivative with respect to x of x to the 2/3 minus 1. I'm using this form as opposed to this form because in this form I can use my power rule. So I bring the power down and multiply by x to the 1 less power. 2/3 minus 1 is negative 1/3, and the derivative of negative 1 is 0. Now you might be tempted to say f prime is well defined for all x in this interval, but remember, negative exponents can be rewritten this way. If you have x to a negative power, that's 1 over x to the same power but positive. So this is really a 2/3 times 1 over x to the 1/3. And if I multiply straight across, I get 2 over 3 times x to the 1/3. That's f prime. And we're going to have a problem when x equals 0. This is undefined. So the conditions of Rolle's theorem do not apply. F prime is not continuous at x equals 0. Or excuse me, f is not differentiable at x equals 0. So we'll say, let's say that first. F prime is undefined at x equals 0. And if f prime is undefined, what does that mean? It means the original function f is not differentiable at x equals 0, and x equals 0 is in the interval from -8 to 8. So we've got a problem. So Rolle's theorem does not apply. So remember, the function has to be defined on a closed interval, f has to be continuous and differentiable, and the y values at the endpoints have to be the same. Okay, last one. I'm right here. I'm going to check my 4 conditions again. I've got the closed interval from a to b, so we're good there. Now I need to think about continuity. Is there any x value for which this is undefined? Well, yeah. I can't divide by 0, I can't take even roots of negative numbers, I can't take logs of negative numbers or 0, and I've got a factor in the denominator. So f will be undefined when that denominator is 0. And if we solve for x, we get this. we get x equals 1. Now, the fact that there's a denominator does not guarantee that Rolle's theorem does not apply. I need to figure out when that function is undefined, which happens to be x equals 1 in this case, and then look at this. Is x equals 1 on this interval? It sure is. What does that tell us? Well, that means our function is not continuous at x equals 1, and if it's not continuous at x equals 1, it's not continuous on that interval. And if f is not continuous on the interval, then Rolle's theorem does not apply. Now, in order to explain what we just did in example A and example B, I'd like to show you some graphs. I want to show you some pictures. Well, at x equals -8, what we do to evaluate this function at x equals -8, we take -8, we square it, we get 64, and then we take the cube root of 64. Cube root of 64 is 4. So we'll have 4 minus 1, which is 3 at -8. So this is not to scale. And if x equals +8, I square it, I get 64. Take the cube root of 64 is 4. 4 minus 1 is 3. I also get that. And at x equals 0 in the middle, the problem, x value, the y value is -1. This graph looks like this. Looks like one of those birds that children draw in elementary school. You can see why Rolle's theorem does not apply. The y values are the same. The function is continuous, but it's not differentiable at 0. So we're not guaranteed to have a point where the slope is 0 anywhere, because we have a point where the slope is undefined instead. Say, okay, well, what happened over here? Well, this is a rational function. Rational functions are continuous on their domains, but the domain of this one does not include x equals 1. This is defined for all x values except x equals 1. So the graph for this function looks something like this. Now, when x is 1, the numerator is -3 and the denominator is 0. Since I've got a non-zero constant over 0, x equals 1 corresponds to a vertical asymptote. If we're on the interval from -2 to 2, we're starting here and we're ending up over here. Our piecewise function, or excuse me, our rational function is going to have two branches. It's going to have two pieces. It's going to have one piece to the left of x equals 1 and one piece to the right of x equals 1. It's continuous on those pieces, but we have to skip x equals 1. So Rolle's theorem does not apply. Let's see what happens at -2 and 2. If I substitute in -2 for x, if -2 squared is 4, 4 minus 4 is 0. So I have 0 over -2 minus 1. So 0 over -3, which is 0. And over here at x equals 2, I've got 2 squared minus 4 is 0. 0 divided by 2 minus 1 is 0 divided by 1. 0 divided by 1 is 0. And we get this. The graph is going to look roughly like this. And in order to figure out that behavior as x approaches 1 from the left and the right, we'd have to take those limits as x approaches 1 and do the sign analysis as we did earlier when we studied these functions. So you can see why Rolle's theorem does not apply here. We've got the same y values at the endpoints. The function is continuous and the derivative is well defined anywhere the function is defined. but the derivative is not defined at x equals 1 because the function has an infinite discontinuity at x equals 1. So Rolle's theorem does not apply to this one. So if the function fails to be differentiable, we've got a problem. If the function fails to be continuous, we've got a problem. And then let's look at that last example again. This is a polynomial function. And there are going to be other functions that have the same behavior or same properties. This one is continuous, differentiable, and we were defining it on a closed interval from -2 to 4. Since it was continuous and differentiable, and f of -2 was 0, and f of 4 was 0, so the y values are the same on both sides, we were guaranteed there must be some x value in between this x value and this x value where the slope is 0. That's what the theorem told us. In order to find that x value, we had to take the derivative, set it equal to 0, and solve for x, and then remember, we're only interested in those x values between -2 and 4. We weren't even interested at -2, which was on that end. In order to graph this, I had to find the y value that goes with this x value. But this part tells me I've got a 0 slope at x equals 2. To find the y value that goes with this x value, I had to replace x with 2 in the original function because this gives me the y values. The derivative gives me the slope. So that's Rolle's theorem. In the next video, we're going to study the mean value theorem, which is very similar to Rolle's theorem. We won't have to talk so much about the details because it's just sort of a natural extension of Rolle's theorem for when the function values at the ends are not the same. So that's your mean value theorem teaser.